Today I want to go over the information you need when you are solving your work, kinetic energy, and potential energy math practice problems. So I have some information to go over first as some reminder things, and then I want to do some practice problems with you. It might be a good idea if you have a pencil and a paper and a calculator so that you can do these problems along with me, get a little practice, review the video more than once if you need to, and then you should be good to go to do the rest of the problems on your own for your actual assignment. So before we get started, let me get myself set up here, and I think we're ready to go. Okay, before we do anything with actually solving the math problems, you need to remember a few of the types of measurement that you'll be working with in these problems. I want to go over the type of measurement that you might see, the variable for that, which is what you would find in the equation, the unit, which is what you would write after the number, and the abbreviation for that unit. Let me get that guy out of the way, and let's get started. So distance is one of the variables that you might see as a type of measurement for these problems. Distance, if you see that in an equation, the variable is going to be lowercase d. The unit for distance is meters, and the abbreviation for meters is lowercase m. So if you see something like 25m, you know it's 25 meters, you can come back here and remember, okay, 25 meters is a distance. The next term, height. The variable in the equation will be a lowercase h. Again, you measure height in meters, and unit abbreviation is m. Work is either a capital W or a lowercase w. The unit for work is the joule, which is a capital J because it's named after a person. Force, the unit for force is the Newton. And capital N, again, named after someone we know. Potential energy. The variable you find in an equation for potential energy is capital P, capital E, or sometimes you will also see capital E, lowercase p. The reason it's often written like this, especially as you look into higher level textbooks, the reason it's written like this is because you're measuring energy. When you measure energy, there are many kinds of energy that you can measure. It can be potential energy. It can be kinetic energy, thermal energy, chemical energy. So, but the main thing, all of those are energy. So we use a subscript, little p, to identify what kind of energy we're talking about for that particular problem. However, your textbook uses capital P, capital E. So either one of these are correct. The unit for both work and energy is the joule. And we already stated that that is a capital J. Kinetic energy, I know it's hiding down here, your textbook will show capital K, capital E, but like I just talked about, we are talking about an energy, and this particular kind is kinetic. All work and energy is measured in joules, so our unit is joules, and the abbreviation for that is J. So if you were to see 45J, you would know that it was talking about 45 joules. Now that could be kinetic energy, potential energy, or work. So you would have to use context clues from the problem to figure out what it was really talking about. Okay, we have a few more of these to do. So let me scroll down. We'll go over velocity, mass, gravity. We'll go over our equations that we need to use, how to use the triangle for work, and then we'll start some practice problems. Okay, we just finished kinetic energy. The variable for velocity is a lowercase v, not a capital V, that would be volume. If you're measuring velocity, that would be like measuring speed. So your units are meters per second. And that is abbreviated like this. Mass is a lowercase m. Remember, mass and meters have the same abbreviation. However, one is a variable found in an equation like down here. One is a unit found after a number. If you were measuring mass, the unit would be in kilograms, and the abbreviation for that is kg. Gravity. Found in an equation, gravity is a lowercase g. Since gravity is an acceleration, the units are going to be in meters per second squared, but all of the problems you will work with are talking about the gravity found on Earth, which has a specific acceleration. So you need to know the number as well as the unit that goes with it. 9.8 meters per second squared is gravity. And we don't need to fill in the abbreviation because I already abbreviated it over here. Okay, having gone over the types of measurement you're likely to see, the variables you'll see, the units we use, and the abbreviation for those units, let's go over the equations for work, potential energy, and kinetic energy. Okay, when you use the triangle for work, remember that you are covering up the variable that is your unknown. So if the problem asks you to find work, you would cover up work, and that means you are left with force times distance. There's no line between the F and the D, so that means you are covering up the force and the distance. If you were looking for force, cover up the F, and then what do you see? W, a line, and then D. That indicates that you are taking work divided by distance. And last but not least, if you are finding distance, it's the opposite, work divided by force. Keep in mind, if you are doing any sort of division problem with these three variables, work is always in the numerator. Whether it's the bigger number or not, you're using your calculator to figure out the actual amounts. So don't worry about whether it's the bigger number or the smaller number. Just make sure you have work on the top, which means you're looking for the unit joules when you're looking in the problem. Okay, kinetic energy and potential energy, a little bit different. Kinetic energy is 1/2. As a decimal, 1/2 is 0.5. If you use 0.5, this entire problem is multiplication. There's no division. 0.5 times your mass times velocity squared. You should know that if you square a number, that means taking the number times itself. So it's velocity times velocity. So when figuring out kinetic energy, you're doing 0.5 times mass times velocity again. And that will give you the correct answer. You could also figure it out this way. Kinetic energy equals mass times velocity divided by 2. That will also give you the correct answer, and those two answers, regardless of how you figure them out, would be the same. Potential energy is also a multiplication problem. There is no division. There will not be any division for potential energy. When you're finding out potential energy, when the problem asks what is the potential energy of, then your equation would be mass times gravity times height. Remember, gravity is a given number, so you will always be plugging 9.8 meters per second squared into that equation. It's always the same number. And the problem will not give that to you. You'll have to remember it's 3 items, mass times gravity times height, and gravity is always 9.8 meters per second squared. Okay. Let's move on to doing some practice problems. If I scroll down here, our first practice problem states, calculate the amount of work done. Okay, what am I finding? Work done. I'm going to go ahead and plug that in now since I know it. Work. That means for the rest of the problem, I'm looking for work. The equation for work is from our triangle. Work is on the top, force times distance is on the bottom. Okay, so that means if I'm looking for work, I have to know force and distance. Calculate the amount of work done when a crane uses 4,116 newtons of force. So what is our force? Remember, you need all three of these items to get credit for the G step in the guess problem. Calculate the amount of work done when a crane uses 4,116 newtons of force to lift a wrecking ball 30 meters off the ground. If you're lifting something 30 meters off the ground, what would that be? Well, look at your triangle. Your options are work, distance, or force. We've already used force. We know we're looking for work. So that means 30 meters must be our distance. Okay, our equation. We're looking for work. So if you cover work up, get rid of it, pretend it's not there, then we're left with force times distance. Work equals force times distance. When we fill in our equation, when we substitute, we have 4,116 newtons times 30 meters. And now let's pull out the calculator. 4,116 times 30 meters equals, actually, 123,480 joules. That is a lot of work. Okay, let's move on to our next practice problem. How much potential energy does the wrecking ball now have if its mass is 420 kilograms? That sounds to me like I might need some information from this first problem, so I'm going to leave that pulled up there. How much potential energy? That tells me, hey, potential energy is my unknown. So I'm going to fill in the rest of my blocks so I don't forget what I'm looking for. Potential energy equation is PE equals mass times gravity times height. M times G times H. So that means I have to have an M, a G, and an H in this step. What is my mass? What is my gravity? And what is my height? Let's take a look back at the problem. How much potential energy does the wrecking ball now have if its mass is 420 kilograms? So my mass is 420 kilograms. I'm going to fill that in. Let's go back and figure out what the height is. From our first problem, we saw that the wrecking ball was lifted 30 meters off the ground. If you lift something 30 meters off the ground, that would be your height. And gravity. Remember, that's one of those given pieces of information that's always the same. 9.8 meters per second squared. If the wrecking ball fell, that's the acceleration it would achieve. Now let's go ahead and fill that into our substitute part of our problem. So we have mass is 420 kilograms times 9.8 meters per second squared times 30 meters. Don't forget that's a decimal. And before we finish that answer, let's pull up our calculator and plug that in. 420 times 9.8 times 30 meters. 123,480. 123,480 joules. Energy and work are both measured in joules. I wonder, that's exactly the same answer we got for the first problem. That's because when you do work to lift an object, you are giving it potential energy. The more work you do, the more potential energy the object gains. So those numbers should be the same. All right, let's look at our last problem. Our last problem is going to talk about what if the chain on the crane suddenly snapped, letting the wrecking ball fall to the ground at 24.24 meters per second. How much kinetic energy would it have? All right, so still talking about the same wrecking ball. Let's go back and plug in some information. If the chain suddenly snapped and the wrecking ball fell, we're looking for how much kinetic energy would it have. So our unknown is kinetic energy. What do we remember the equation for kinetic energy being? I'm going to use mass times velocity, or mv squared divided by 2. Now let's see if we can fill in the given information. Oops. Kinetic energy is what we're looking for, so we don't already know it. Mass, and we need to know velocity. The mass of the wrecking ball came from question 2. What is it? That's right. Its mass is 420 kilograms. The velocity is given in this question number 3. We know velocity is measured in meters per second, so 24.24 must be the velocity. Good. Now we can fill in our information. Mass is 420 kilograms. I'm going to move up here so I have a little more room to write. 420 kilograms times a velocity of 24.24. Remember, the velocity is squared, so 24.24 again. All of that divided by 2. If you remember anything about order of operations, what do we have to do first? That's right, we have to do the multiplication part of the problem first. So, let's pull up the calculator and do 420 times 24.24 times 24.24. Press enter or equals before you move on to the division part of the problem. That tells the calculator, okay, I've got this part of the problem is done, now I need to divide that by 2. And we are left with what looks like a really large number, 123,391.296. Since this is in the nearest hundredth, let's round our answer to the nearest hundredth as well. So remember, back from rounding, we need to look at the thousands place in order to round to the hundredths. The thousandths is a 6, which would round the 29 to a 30. So 123,391.30. And just like work and potential energy, the units for kinetic energy are joules. Wow, that is a lot of kinetic energy right there. All right, we've done a potential energy problem, a kinetic energy problem, and a work problem. I've showed you how to use the triangle if you are asked to find force or distance instead of work. If you have any questions, make sure you send me a message or ask me. And don't forget, you can always go back and view this video again if you need help solving any of the problems on your assignment. Good luck!